Okay, so hello everyone. Welcome back to this live problem solving session uh, for the course Essentials of Topology. So this is week 3 of this course. So before going to solve some problems, if you have any doubts, just ask and I will try to solve them. So from the lectures, do you have any doubts so far? Okay, so first, just let me quickly write down the contents of this week. Meanwhile, if you have any doubt, just feel free to ask. So, in the second week, we end up with defining basis for a topology. And in this week, we started with an arbitrary collection of subsets of a X, and we checked when it forms a basis for some topology. So some notions related to basis. Also, we have seen couple of examples, and we have seen how to compare topologies using their basis. So I will come to some problems related to this so that it will be easy to understand. So comparison of topologies using basis. Then we have seen some topologies on R2. And after that we have defined subbasis, and we have seen few examples. Then we have constructed various sets in a topology. The first thing is like when we say a set is neighborhood of some point, and in terms of neighborhood we have characterized open sets, and also we have seen some properties of this neighborhood. And after this thing we have defined limit points of sets, and if you have a set A in a topological space x comma tau, then the set of all limit points we have denoted it by A prime, and it is usually known as derived set of A. So I will just write derived set. And some examples of these things and some properties. And we have also characterized closed sets in terms of this derived set. And after that we have defined closure of a set, and properties of these things, and what is the relation between derived set and the closure. So we'll see some problems also related to this, and after that, uh, dense sets and their characterizations. So I hope all these topics you have already seen in case of metric spaces or in real analysis, but we have defined these things in more general setup in a topological spaces. And after that, interior of the set and interior points, some examples and properties of these sets. And finally, we have defined boundary of the set and their properties. We have seen their properties. So this is the overall topics of this week. So feel free to ask if you have any doubts from these topics or even from the first or second week.
Sir, when we are going to find out interior of a set, for suppose X is given A, B, C, D, and we are defined some topology, and one set is given. In the interior, how it is? I'm getting little bit confusing, sir. For suppose A, B, D, while sir are doing in the class, a set A is equal to A, B, D defined, but in the topology there is no set contain open set A, B, D. So A interior is empty, sir has written. And one more example.
Sorry,
A
which example?
means while defining after defining interior of a set, sir has given just an example. Means that after the definition itself.
Can
Just
you tell me which example exactly the
yes.
which?
Before the interior definition, after the interior definition only, sir is going to define the topology X equal to A B C D.
Yes,
Then
yes,
and that only, sir. I am getting for first it will be A interior is empty and B interior it will be something.
yes.
Means how it is means interior means in a set they given what they given that any two elements they are containing that is defined as interior. I am
So,
getting there little confusion,
so
sir.
did you understand the definition of the interior properly?
Yes, sir. Means
So it is the
largest
largest open set
set.
contained in that set. Okay.
Yes,
Now,
sir.
maybe I will just write that example. Uh, so there X is the set A, B, C, D, and E, and the topology was empty set, whole set. Uh, the set A comma B, the set B comma C, singleton set B, and ABC. Okay, so now if you take A as A, D, and E, then the interior is going to be empty. And if you take B as A, B, D, then interior of B is A comma B. So in which one you have doubt?
So in first one why it is empty, whereas in second one why it is a
So,
comma B.
so how to find this interior? So what you can do is you just find the open sets which contained in A and you take their union. Can you find any open set from tau which is inside A?
No, no, sir.
Only empty set is there.
Yes, sir. Sir, since if singleton A is present means then it will be singleton A. If at least singleton A open set is present means then we are going to write that itself.
Yes.
Means
So
in the case.
suppose from tau 1 you got two open sets, A1 and A2, and both A1 and A2 are inside A. Only these two open sets are there. Then you take their union. That will be your interior.
Okay, sir. Okay, sir.
So
Yes.
you take all open sets which are inside A and take their union.
Okay, sir. Thank you, sir. Thank you, sir.
Yeah. Anything else? Any other doubts?
Sir, does there exist a finite dense set? Somewhere I read a question. Does there exist a countable dense set in a metric space? That is what they asked, sir.
In a metric space, you are saying.
Means any topological space we are going to define. Does there exist a finite dense set, and what is the topology we call the topology they are asking?
Actually, your question is not clear. So can you
Okay, sir. For 1 minute, sir, I will bring that book. I read somewhere that question.
maybe you can put it in the discussion forum also.
Okay, sir. I will give that.
Okay, if you people have no other doubts, maybe let's solve some problems. Okay, so let's solve some problems first from the concept of basis. So the first one is first consider the set of all natural numbers and say it is x. Then which of the following are bases uh, on x? So the first collection is so G subset of X such that each element of G is an odd number. The second one is all those subset of X such that each element is is a prime number. So each element of G, so the third one is your B3 is you take the sets of this form 1 to up to n, where n belongs to the natural number n. And the last one is all those subsets of X such that uh, G is a finite set and exactly half of the members of the elements or of the members of G are even numbers. So you need to check which collection forms a basis for some topology. So you are saying option C, but
So what is the topology?
no, this is an arbitrary collection. This so you need to check this forms a topology, sorry, this forms a basis for some topology or not. So how to check this thing? Suppose, okay, maybe I will write here in. So suppose you have a non-empty set X and you take a collection of subsets. So how to check this B is the basis for some topology or not? So we need to check two things. First thing is this,
The whole set.
yeah,
Union of,
yeah.
yes.
If you take the union of the members, then it should be the whole set. That is the first condition. And the second one is if you take two elements from the basis, and if you take a element from their intersection, then there must exist another basis element such that X should be inside that basis element and B3 should be inside their intersection. So these two things you have to check. Then B will be a basis for some topology, and that topology you can deduce from this basis itself. So which one you think will be a basis? So one person is saying option C, but can you say why the other options are not basis?
So union
Sir, in
or
option
option
A,
A.
Okay, let's see one by one. What about the first option?
sir, in option A, every element in G is given to be an odd number. So if we
Yes.
take the union of arbitrary number of G, it will not be equal to the set of natural numbers because even numbers are not in the set.
Yeah, right, and right.
And in the second set, in the second B2, every element is prime in G, so that will the union will also be a basic set of primes. So it will not be equal to n.
Okay, so for A and B, the reasons are exactly same. The union will not be the whole set, and
So,
yeah,
so I didn't check for the fourth one, but I think third one should be correct because the union of we take the union of one to sets one to n, then it can be we form the it is equal to the set of natural numbers, and any two subsets we take the intersection, then there is always the intersection is always in B3.
intersection is always
In
B3.
B,
Intersection is always empty.
why is it?
No, sir. Intersection is always finite and there exists a
Yeah,
finite
actually
set.
the intersection will be the smaller set.
Yes, sir.
Okay, so let me write down for B1 and B2. B2 check that uh, union of the members will not be the whole set. Okay, will not be X. So C will be a basis. So answer is C. B3 is a basis. So the first thing is, so if you take union of this type of sets where you are having all your natural numbers, then this is clearly your set of all natural numbers. This is just set theory. You can prove both inclusions. And the other thing is if you take intersection of these two things, then this will be just 1 2 dot dot n, where n is just minimum of n1 and n2. So now if you take a point from the intersection, then that point has to be in the smaller one. That is already a basis element. So you don't need to put much effort in that case. And what about the fourth one? So what about the first case? Does the union of these members gives the whole set?
No, sir.
It is not giving the whole set.
No, sir.
Sir, since
Why?
they said only half the members should be even, but the freedom left was, why can't I take remaining half should be odd?
So union is not the whole set.
No, sir,
Why?
this condition will satisfy. Why? Because they only mentioned about half should be even.
Yes.
They said nothing else.
Then the
But
other
G
half
should
should be
be
odd
finite,
numbers.
they said.
Yes, all these basis elements are finite, but their union, is it the whole set?
Sir, this is true.
So 2 means the union is whole set or it is a basis?
Yes, sir. I think so.
Means which one you are saying true?
Sir, D. B4 is the basis for n.
Can you give some reason why or
Sir,
justification?
union is whole set and the first condition is satisfied.
How?
How?
How means? Can you give some easy reason that why the union is the
Uh,
whole set?
so take sets 1, 2, 3, 4, 4, 5 like this and take union, arbitrary union, you will get the.
Yes, so basically what you are saying is, so n can be written as, so if you take any natural number n, it does not matter it is even or odd. If n is odd, then n plus 1 is even.
Well, sir.
And if n is even, then n plus 1 should be odd. And if you take just this double tone set, then exactly one element is odd and other element is even. And you take their union, then it should be the natural number. But what about the second condition? See,
So
the second
second
condition
condition is
will not hold.
also satisfied, I
No,
think.
no, it is not satisfying. So you see, these elements are in the basis. So you take 1 comma 2 and you take 2 comma 3. These two elements in the basis. And you take 2 from their intersection.
Yes, sir. Yes, sir. Correct.
2 from their intersection. Actually, 2 is equals to their intersection, but 2 is not in the basis element. So the second condition will not hold. So before is not a basis. So uh, did you get the?
Not in the basis, or there does not exist any basis element which contains this.
Yeah, eventually that is the thing, but since this intersection itself is 2, so you will not get any basis elements which is inside the intersection containing 2. Yeah, any doubts or any queries?
The thumbs up.
No, others, any doubts? Okay, so the right answer is the option C. So option C is a basis. I think you have already seen this topology in one of the lectures. This is the initial segment topology, I think. Okay, maybe let's move on. Okay, let's see one example on R2 maybe. Okay, so let's write down this. So let's consider the set R2, then check which of the following are basis for some topology. Okay, the same type of question, the set and the collections are different. So the first option is you take B1 as all those sets GM subset of R2. So where GM is defined like uh, it is the straight line such that X belongs to R and M is belongs to R minus 0. Okay, so GM is basically a straight line and you take the collection of all straight lines in through origin. And B2 is basically all those subset of R2 such that G is a square of side length, let's say L for some positive real number L, and with one more condition. So G is a square whose length side lengths are L, but there is one more condition. This is the top left vertex of the square. Uh, the top left vertex will be at x comma y for some x comma y in R2. So check only for these two collections. So maybe we'll try one by one. So the question, I hope the question is clear. So let's try to understand the first collection. So how an arbitrary element of B1 looks like. So it is a
Straight line passing through origin.
yes. So if you take the Cartesian plane, this is the x-axis, this is y-axis, then it is just y equals to mx. So this is y equals to mx. So this is your gn, right? So you take all straight lines, then that is your collection B1. So is it a basis for some topology?
No, sir.
Why?
Sir, second condition will not be satisfied because origin will be there and intersection of two straight lines passing through origin will be origin and
Yes. So this is your x-axis and this is your y-axis. Now suppose you take this line, let's say y equals to x, and let's take another line, y equals to x by 2. Sorry, this will be the origin. Then these two straight line intersects at the origin only. So B1 is not a basis because you take G1 and G1 by 2 according to our notation. So Gm, where m is equals to that real number. So because the origin is equals to the intersection of G1 and G1 by 2. So you cannot get another basis element which is a straight line. which contains in the intersection, right? Because the intersection is just a singleton set. So there does not exist some G M belongs to B1 such that origin is in that GM and it is subset of G1 intersection G1 by 2. Because GM is the straight line, it is an infinite set, and your intersection is just a singleton set. Okay, B1 is not a basis. Now what about B2? So the first option is clear, right? That B1 is not a basis. Okay. Uh, so let's see the elements of B2 first. Then maybe we can try to answer it. So
Sir, how you are saying there does not exist a GM? Why? Because there are infinitely many straight lines which are passing through origin. In
so
between
if
that also there may
so
exist a.
every GM is an infinite set, right? So an infinite set cannot be a subset of a finite set. Uh, is it okay? Are you getting?
So the intersection part means there should exist in between that there should exist one line. It should contain.
So in the intersection, I have taken one point. Can you find a GM which contains the origin and it is also contained in the intersection? So this GM, it is an infinite set. Whatever M you take, it will be an infinite set. But this intersection is singleton. So, so infinite set cannot be a subset of a singleton set.
Yes, sir. Yes, sir. I got it, sir.
Yeah. Okay. Okay. So what about the elements of B2? So if you look at the plane and it is a square, every basis element is basically a square. So it will looks like this, and the top left end point it is x comma y, and this side length is L, and you take collection of all squares of this form. Then is it a basis or not? That we have to check. You are saying
Yes, sir.
yes. Uh, okay, so how?
Sir, union is sir R2. So first condition
Yes.
is satisfied.
Yeah, so it
And
was one of the example. No, that example is little bit different. So here the case is we have additional condition. The top left vertex is at x comma y. Okay, so we have this additional condition. So you have to take care of this thing. So the union is R2, that is clear. So R2 is union of B such that B belongs to B2. So let's try to check this one by drawing the images. Okay, so so how to prove this equality? So this containment is clear because every B is subset of R2. So this containment is clear. But what about this containment? So from the plane, if you take an arbitrary point, let's say a comma b, then you can find a square, right? You can find a square which is inside uh, such that the point lies inside of that square, and you take an arbitrary top left
Sir,
endpoint. Then
sir,
you take this, yes.
sir, can we consider a point as a square?
No.
Why?
So can you consider a circle, a point as a circle?
De- Degenerate case, sir.
No,
Consider in
there should be some radius, right? There should be some positive radius.
okay, sir.
So the length, here you see, I have mentioned a square of side length L, and L is positive. So if the length is positive, you cannot consider a point as a square. So what I am saying is, if you take a point AB from R2, you can always find a square like this, and that square will be in a basis set. So this containment is also clear if you see it pictorially. So I am not going to write rigorous proofs. So I will just check this pictorially, because in most of the cases you can draw the images and check things if they forms basis or not. Now what about the second one? So for second one, if you take two elements b1 and b2 from your script b2 and an arbitrary point from their intersection, so the image will be something like this. Okay, so b1 is some let's say here, so it is not looking like a square. Okay, so this is your b1 whose top left endpoint, let's say it is just x1 y1, and you take another, maybe let's say here, this is your b2. So here the top left endpoint is x2 comma y2. Suppose so your intersection area is this one. Okay, only this much. Now you take a point, let's say here, a comma b. So can you find a basis element containing this AB, which lies inside this intersection?
Yes, sir.
Yes, sir.
Yes. So pictorially it is easy to see, right? So you can find a smaller square which lies completely inside the intersection and contains the point a comma b. So it is definitely a basis. So you can also prove this rigorously, but let's not do this, because you can do this, you may try to do this, and it will take much time, and I want to do some other problems, so I will not go do that thing. So the correct answer is B. Okay, any questions so far? Maybe let's do one problem from those exams. This is problem number 3. Okay, so let okay, maybe I will rewrite this so that it will be easy to understand. So let tau e be the Euclidean topology on R2. Okay, and I will define one more topology. So before that I need some notations. So given small r and big R from the set of all real numbers with 0 less than small r less than big R and a point from R2, let's say A1 comma A2, from R2 let C. Okay, so this is your small a, the point. So C a comma small r comma capital R is defined as uh, all those points from R2 such that small r square is less than x1 minus a1 square plus x2 minus a2 square less than big R square. Now define, let tau be the topology uh, on R2 generated by this mm, generated by, let's say, all these sets of this form C, A, R and capital R. Maybe I'll write here. Generated by all these kind of sets where A belongs to R2, R and small r belongs to R with 0 less R, this condition. Then we need to compare these two topologies and how we will do that. So first one is tau Euclidean is proper subset of tau, means tau Euclidean is coarser than tau. Second one is tau is coarser, strictly coarser than the Euclidean topology. Third one is both are equal. And fourth one is they are not comparable. So neither tau e subset of tau nor tau subset of tau e. Okay, so let's try to understand this problem. So tau e is the Euclidean topology on, okay, sorry, this is R2, Euclidean topology on R2. It is already defined in the lectures. And we have seen couple of bases for this topology. So it can be circle, it can be rectangle, it can be square, or it can be diamond shape objects. So you can consider with any kind of basis. That will be the Euclidean topology. But the second one is the topology generated by this kind of sets. So how this sets looks like. So from this inequality, this is inside of a circle, and from this inequality it is outside of a circle. So basically if you draw the picture, let's say you have a point here and you have a circle of radius, let's say small r, and you have another circle of radius big R, then what will be that set? It is just this inside of these two circles. Okay, so this is this annular region. So these your basis elements for the topology tau. So in the lectures we have seen how to compare topologies using basis. So can you use that to find the answer of this?
Sir,
Yes.
the second one is strictly contained in Euclidean topology
Uh, why?
because take any point in the set you you just drawn
Okay.
annular region, you can always find a square which is
Okay.
always inside in that annular region.
Yes.
So
So
tau is
so your tau e is subset of this tau, but why it is strict?
sorry sir, tau is Euclidean topology, na? Tau is subset of tau e.
Okay. So tau is subset of tau e.
Yes,
How
sir.
you are saying?
So there is a theorem, na? If for
So you take a
every
basis for this Euclidean
uh,
topology of squares.
for every element in the basis, if you get a element from other topology,
Okay.
basis of a topology which is contained in that basis element, then this will
So which one you are saying?
tau is subset of tau e.
So to prove tau is subset of tau e, okay, maybe let me write down that statement first so that it will be clear. So we will write maybe in be here. So so suppose you have two topologies. Uh, let's say X is a non-empty set and let's say B1 and B2 be two bases for tau 1 and tau 2. Now we want to compare tau 1 and tau 2 using B1 and B2.
Yes, sir.
So suppose you want to prove tau 1 is subset of tau 2, then how you will use the basis? So what you have to show, uh, every element of tau 1 is in tau 2. So if you can prove that every basis element of tau 1 is in tau 2, that is enough, right? Because every element of tau 1 is union of elements of B1. So see, so the first thing is, so to show this, the first thing is every element of tau 1 is union of members of B1, right? That is the definition of basis. So it is enough to show that B1 is inside tau 2. That will be enough. But how to show B1 is inside tau 2? So now even it is enough to show every element of B1 is union of members of B2. Is union of members of B2. So that is the thing you have to finally show. So now if you take an arbitrary element, let B from B1, and we want to show it is an element, it is union of members of B2. So let X belongs to B and find some B prime inside B2 such that X
X belongs to
belongs to
B
B
prime
prime
subset of
subset
B.
of B. Yes. So it is the reverse way actually.
Yes.
So for if you want to show tau 1 is subset of tau 2, you take a basis element from tau 1, let's say it is B, and you take an element from B, then you need to find a basis element of tau 2 such that X is contained in that basis element and that one is contained in B. Okay, so you have seen this statement in the lectures to compare topologies using basis, but it is just using the original definition. You have to just reduce it step by step. So I have said too much actually here, but it was not needed. It's okay. So now using this, can you compare these two topologies? So let's do it. So in our problem, maybe let's consider let's consider the basis consisting of circles for the Euclidean topology. Okay, now we have two bases. So let's prove both side inequality. Actually, these two topologies will be equal. So let's do it pictorially. How to do this? So take a basis element of tau e. Uh, so let's take a circle. So this is a basis element B from tau
Circle
e.
of open disk.
Yes, it is an open disk. Now take a point inside of this disk, maybe any point. So can you find a basis element from the other one?
Yes, sir.
So it is now you can see that you can find a annular region like this. So it is clear from the picture and this annular region contains your point and it is in your other basis. So this gives your first inequality. So is it okay? Is this clear? Okay, now the other part. So tau is subset of tau e. So for this, we have to take a basis element of tau. So let's take an annular region. Okay, so this is an element, let's say B prime. So here B prime is subset of B and your point that is contained in, maybe I write, let's say it is X. So X belongs to B prime here and here you have taken a point X. So can you find a circle which contains X and lies inside this annular region? So that is true, right? So you can find a smaller circle. So maybe the picture is not good, but I hope it is understandable. So this will be your B prime. So then X belongs to, sorry, I am using the same notation. I should. So you have taken B prime and you want to find B. So X belongs to B subset of B prime. So this proves this other inclusion. So these topologies are equal. Okay, so before giving rigorous proof, try to do it pictorially. It will easier to understand if you draw the images. So the right answer is the option C. So is it okay?
Yes, sir.
Okay. Okay, then let's move on. So there are other problems related to basis, but those are easier. Uh, Maybe I shall move on to other topics. Maybe. Okay. So we have defined various kind of sets. Maybe of problem. Maybe let's just discuss this. So quickly, let me give you the overall picture so that it will be easier to solve the problems. So let's take a topological space x comma tau. Okay, and let's take a subset A inside X. So this, from this set A, we have various sets. So the first one is A dash, set of all limit points, derived set of A. The second one is A closure, closure of A. Third one is A naught, interior of A. The fourth one is del A. So I hope we have used this notation for boundary. So for boundary of A. So this is set of all limit points. So elements of A dash are limit points. And what about A closure? So if we take a point from A closure, what do we call this? So this we call set of all adherent points. Adherent points of A. And what about A naught? This is set of all interior points of A. And this last one is the set of all boundary points of A. Now, using A dash and using A closure, we have already characterized closed sets, right? So the first one is A is closed. Maybe I'll write here. A is closed if and only if A dash is subset of A. This we have already proved, and also we have proved this A is closed if and only if A bar is equals to A. So there is one more condition that you may try to prove, that this is true if and only if the boundary is contained in A. So A is closed if and only if A contains its boundary. Now for open sets, we have proved A is open if and only if A equals to A naught. So these are the conditions. Okay, maybe. So I hope you can recall all these things from the lectures. Maybe let's write down some problems. So this is problem number, I think, 4. So I think cofinite topology is in the assignment. So maybe I will do for the co-complement topology. Sorry, co-countable topology. So find closure and derived set in the following cases. So here your topology is, the set is R, and you take the co-countable topology. So the first set is the intervals. All kind of intervals. The second one is a finite set. Third one is natural number and Z. Fourth one is rational number and irrational number. And fifth one is this 1 by n such that n belongs to n. Okay. So in each cases you have to find the closure and the derived set, where your topology is the co-countable topology. So let's start with the first one. So what will be the derived set? So we know if we can find the derived set, it will be easy to find the closure, right? Because for any set A, its closure is just A union A prime. You just take A and take the union with the derived set. That will give you the closure. So let's find the derived set. So what will be the derived set for this open interval A, comma B? Yeah, any idea?
Sir, its complement should be countable now. Since it is not, its complement should not be countable. So here it will be empty.
Sorry.
Since its complement should be countable, or set should be equal to x. That is how topology we are going to define.
Yes, the co-countable topology.
Yes, sir. So here the open interval AB is infinite and its complement is also not countable.
Yes.
So this does not belongs to the set. So the limit point should be empty. What I am saying, empty for my side.
But why empty?
Since the elements are not belongs to the set, the open interval AB is also does not belongs to the set. If we do the
Does
limit
not
point,
belongs to the set means what?
means it is not in the co-countable topology.
Open interval AB is not in the co-countable topology. Yeah, that is fine.
So the limit points, set of all limit point means intersection with the set should be non-empty. Means if we are going to
if
take
you
any
take
point
a point from the
and
space, and if you want to check it is limit point or not, you need to see that if you take any open set which contains X, then you just remove X from that open set and you intersect with the set A. That should be non-empty. Then it will be limit point. And this should true for all open sets. That is the definition. So are you using that one?
yes, sir, that is the house. Means the open interval ABs does not belongs to the set. Means where should we are going to take any element from the set, means in real line, or we are going to take also this condition will not satisfy.
I'm not getting actually how you are saying, but let's see what how I was thinking. So I will do it for general case. So what I will do is before coming to these cases, I will write down a general case. So let A is subset of R. Then we have two possibilities. Either A is countable or A is uncountable. So suppose A is countable. So in both cases, I will find the derived set and the closure. So in this case, my claim is the derived set is empty. Why? Because if you take any point, let X belongs to R. Okay. And take a open set which contains X. So maybe you can take R minus A union singleton set X. Then this is in the co-countable topology, right? Why? Because your A is countable. So you are removing a countable set from R and you are just adjoining one element. So this is this what is complement of this set? Can you say?
Yes, sir.
So complement of this set is A, that is countable. So this has to be an open set. But so let's take G as this. So then if you remove X from G and if you intersect with A, then what you will get? So it is basically R minus A intersection with A. So this is basically A complement intersection with A. So it is empty. So you found an open set which is not satisfying the criteria for limit point. So this means X cannot be in your derived set and your X is arbitrary. Right? So this will imply A dash is empty. And that will imply A is closed. So every countable set is actually closed. That is from the definition, but the derived set is empty. Now what about the second case? A is uncountable. Then what will be your A dash? So first of all, the closure, it is easy to see. What will be the closure? So what are your closed sets in co-countable topology? So because in co-countable topology, the closed sets are only the whole set and countable sets. And your closure is the smallest closed set which contains A. So what will be the smallest closed set which contains a uncountable set? That is R, right? And because A is uncountable, so the smallest closed set which contains A is only R. So the closure will be R. But what about the derived set? So the point is the derived set is also whole R. Can you see why? So if you take an arbitrary element, can you prove that it is a limit point? Yes. So let's prove that X is a limit point. So for that, let's take a open set such that X is in G. And what we have to prove is this G minus X intersection A is non-empty. So is it non-empty? Okay. See, G is a open set in the co-countable topology. That means G complement, which is some countable set. So let's take G is R minus C. So we are removing a countable set from R. So if you take G minus X intersection with A, so this is basically R minus C union X, and you are taking intersection with A. Can this be empty? So this part is countable. You are removing a countable set from R, then taking intersection with an uncountable set.
It is always non-empty.
So is it true? So what happens if you take C equals to Q and X is equals to, let's say, 1? let's take C equals to Q and your X equals to 1, and let's say your A is equals to R minus Q. So you are removing C from R, then that is exactly R minus Q. Yes, so it will be always non-empty. So because you are removing only countably many elements, so this implies X belongs to A dash. So every real number will be limit point. So for uncountable sets, the derived set is the whole R, and for countable sets, the derived set is empty. So we have only two choices. So did you understand the proof?
Yes, sir. So what about the intervals? These are also uncountable. Means
Yeah,
they are
intervals are
considered as also are
uncountable
equivalent.
except this case. If you take A comma A, then that is a
That will be
finite set.
seen. Yes.
Yeah. So except that case, uh, all are uncountable. So now you can easily answer these things. So maybe let's quickly write down. So these are uncountable, and this is uncountable if and only if A not equals to B. So this is finite set, this is countable. So these two are countable. So Q is also countable, and R minus Q is uncountable. And 1 by n it is countable. So now you can easily distinguish uh, whose closure, whose derived set is the whole real number and whose derived set is empty. Okay, so you just fill out the details by yourself. Maybe let's do one easy problem. So any questions so far? Okay, so this is from GATE 2021. So consider the following topologies on R. So T1 is equals to all those subsets of R such that either 0 does not belong to U or U equals to the whole real number. And T2 is U subset of R such that 0 belongs to U or U equals to empty. And T3 is T1 intersection T2. So we have already seen intersection of topologies. Any number of topologies is again a topology. So T3 is also a topology. Then the closure of 1 in R comma T3 is 1 itself, B it is 0 comma 1, C it is R, D it is R minus 0. Okay, so the question is very simple. So we have two topologies, and third one is the intersection of the first two topologies. So we have a topological space R comma T3. So we need to find the closure of this singleton set in that topology. So how to do this? So to find the closure, we first need to find the closed sets, right? Because the closure is a closed set. So find the closed sets in T3. So before finding the closed sets, we need to know the open sets. Can you find the open sets in T3? So closure is a closed set. So that is first point. So we need to find the closed sets. But closed sets are complement of open sets. So we need to find the open sets. So what are the open sets? So T3 is T1 intersection T2. So what will be T1 intersection T2? So this is so see, it is a topology. So the empty set and the whole real number has to be in the intersection. But it also contains U subset of R such that U belongs to T1 and U belongs to T2. So U belongs to T1, that means 0 does not belongs to U. And U belongs to T2 implies 0 belongs to U. So is it possible? Now what about this one? So U subset of R such that U belongs to T1 means 0 does not belongs to U. So this is not possible, right? So this has to be only, there has to be only two open sets. So the first one is excluded point topology, and the second one is particular point topology. And you are finding the intersection. Is it okay? The intersection? So it is just the indiscrete topology.
Sir, can you show me the question once? I got internet issue. Sorry.
Okay. So on the real number, you consider two topologies. This is the excluded point topology, and T2 is the particular point topology. And you take their intersection and you call it T3. You need to find the closure of a set in T3. That is the question. So for that we need to find the closed sets in T3, and for that we need to find the open sets. And what we have got, T3 is the indiscrete topology. So what are the closed sets? So the closed sets are, there are only two closed sets, the empty set and the whole set R. So what will be the closure of 1? What will be the smallest closed set containing 1? So it has to be the whole real number because there are no other closed sets. So the answer is option C. Is it okay?
So can you explain just for 1 minute again? I got internet issue and the entire thing went off.
So did you understand the problem?
Yes, sir. Two topologies are defined. Tau 1 is an excluded point topology, and Tau 2 is an included point topology. Their
Yes.
intersection is again a topology.
Yes. Then you need to find the closure. So how to find a closure?
Closure means set the union with a set of limit points. A closure.
Set of all.
Uh, A union A dash A closure is equal to, that is
Yeah,
one way, or
that is
set,
what is the definition?
the smallest closure set containing this.
Containing that set, yeah. So can you find the smallest closed set containing 1? So first of all, you need to find all the closed sets. And for that, you need to find all the open sets. So if you check, you will find that your T3 is basically indiscrete topology. So from that, you will get the closed sets are only empty set and the whole R. So the smallest closed set containing 1 is the whole real numbers. Yeah, did you understand?
Yes, sir, I got it. Thank you.
Okay, then let's move on. Okay, so maybe this is problem number 6. 6 or what? Yes. Okay, so maybe I will just rewrite this question. So let X be a topological space. Okay, so X be a topological space and a subset of X. Then which of the following is true? Okay, so the first option is if S is open, then S is equals to the interior of S closure. If the boundary means del of S is empty, then S is open. If the boundary is empty, then S is not closed. And the last option is if S closure minus S is a proper subset of del of S, then S is open. Okay, so we have 4 statements. We need to check which of the following are true. So del of S means the boundary. Maybe I will write here. So del of S by definition it is A closure minus the interior of A. So this is the definition that we have used. Okay. So what about the first option? Is it true?
No, sir.
Yeah. Why?
A set is open if and only if set is equivalent to interior of it.
Yes. So then if and only if it is equals to its interior, then how you are saying?
Means the set will be equal to interior, not closure of their interior. The definition itself is
Yeah,
the
but they
term.
are saying suppose. So suppose S is open. Suppose S is open. So then can this equality hold? S is definitely equals to its interior in that case. But can these two be equal?
Need not be, sir. That is what
Yeah,
means.
do you have any example?
No, sir. Right now, I'm not getting any idea, but mm, means open interval 0 1 in that format can we take, and means it will be equal. Then if we take 0 1
So
means then
let's try to think examples in the real life, in the usual topology with R. Okay. So in R comma tau E, in the usual topology in R, if you take S as open interval 0 1 union open interval 1 2, then this is an open set because this is union of two open intervals, means union of two basis elements. So then S is open. But what about S closure? What is the closure of S? Yes, exactly. The closure is closed interval 0 2. And then interior of S closure is open interval 0 2. So this implies S is not equals to interior of S closure, but S is open. So this is a counter example for the first option. So the first option need not be true. So what about the second one? So if the boundary is empty, can S be open? So what do you think? And only closer of A, so it must be closed. But is it open? Why? So see, so boundary of S, which is basically S closure minus uh, interior of S, and this is empty, that is given. So this will imply uh, interior of S should be inside S closure. Am I sorry? No, not this thing. That is always true. So there is no point in S closure which is not in interior of S. So S closure should be subset of interior of S. Now you recall interior of a set S is always inside of the set S and it is always inside of the closure. So here you will get S equals to interior of S equals to S closure. So S equals to interior of S. So it has to be open. And S equals to S closure. So it has to be closed. So both, it is both open as well as closed. So the option B is true. And C is false. Is it okay?
Yes, sir.
Okay. Now what about the last option? If S bar minus S is proper subset of the boundary, then can S be open? So what is given is S bar minus S is proper subset of the boundary. So can you think of some example in which this condition holds? Try to think some example in the usual topology of R. So maybe let's take S equals to let's take close 0 open 1. Then what will be the S closure? This is whole close interval, and what will be your boundary? It is just 0 comma 1. So S closure minus S, this is just singleton 1. This is proper subset of del S, right? So this satisfying the situation. But what is the statement saying? S is open or not? But here S is not open, right? This set is not open in the usual topology. So this is a counter example for the option D. So you just have to, so if you are not getting anything, you just try to think of an example which satisfying these situations. And not just one example, you try with various examples first, then see what is happening. And if you have already some idea, then try to prove this. That is the idea. So the correct option is option B. Yeah, is it okay so far? So far, any doubts?
No, sir.
Okay. Okay, then maybe we can stop here today. I think sufficient problems I have done. Okay, so maybe if you have no other doubts, then we'll wind up today.
Okay, sir. Thank you, sir. Good night, sir.